Jai Hind everyone. I am Deepak Narang, Assistant Professor, Electrical Department of Ajay Kumar Garg Engineering College. The topic of my today's lecture is Routh stability criteria, which is very important topic for finding the stability of an LTI system. So in this topic, we are going to discuss basically introduction to stability, types of system which are based on stability, pole location and their corresponding transient response, necessary condition of stability, and then how Routh array is formed and their special cases. So first of all, why we go for stability in control system? As we know, the system performance is basically depending upon what kind of output we are getting. If that output is of our interest, then we say that system is stable one. And this basically defines the performance of control system. And any control system can be defined as response of two responses, that is zero state response and zero input response. What is zero state response? The zero state response basically is due to input only. It is not depending upon the initial conditions. And second is zero input response, the response of any system which we are getting due to initial conditions and when input is zero. So by combining these two responses, we call total response of any control system. And roughly speaking, we can say a small change in the input or say initial condition, it doesn't result into a large change in the system output. Then we can say our system is behaving properly in a stable manner. So we can use two notions of the stability which are to be satisfied for an LTI system to be stable one. So first of all, when system is excited by bounded input means when input is in a defined range and output which we are getting is also in defined range, that is bounded. This stability is defined as BIBO stability or bounded input, bounded output. And second is when no input is applied and output tends towards zero irrespective of any initial condition, then system is said to be asymptotic stable. So on the basis of this, we can define system as absolute stable, conditional stable, or marginal stable. Absolute systems, absolute stability means when system is stable for entire range of system component values. Okay, if all the poles of the system are lying on the left half of S plane in both the ways open loop as well as a closed loop, then we call it as absolute stable system. But if system is stable only for a defined range of components, then system is said to be conditionally stable. And next is marginal stable, when system poles are lying on our imaginary axis and these roots are not repeated, then we call it as marginal stable, because system in this system output oscillate with the constant amplitude and constant frequency. We cannot say that system is completely unstable. Rather, we call it as marginal stable or limited stable. So we can define the responses on the basis of our pole location. So these responses which we are getting because of poles which are lying on left hand side of S plane. Okay, so we see when poles are lying on left hand side, the output oscillations are decaying with time, and when pole is on imaginary axis, we can see the response is oscillatory. Oscillatory with constant frequency and amplitude. Here when pole is at origin, we can see no frequency, so we get DC response. But when poles are lying on right hand side of S plane, the output is going beyond its defined range and we call it as unbounded output. And we call system as unstable. System as unstable. So we can define key points for a system to be stable one if all the roots of characteristic equation have negative real parts, that is all the poles of the system are lying on the left hand side of S plane, the system is said to be stable. Second, if any of the root of the characteristic equation has positive real parts, or we can say system is having positive poles or poles lying on the right hand side of the S plane, or there are repeated roots on j axis, j omega axis, the system is said to be unstable. And next, if all the roots of characteristic equation have real negative part except for the presence of one or more non-repeated roots on imaginary axis, the system is said to be limited stable or marginal stable. That is, if we are having roots like this, we can say system is limited stable. So we can derive necessary condition for stability, or we can say just by glancing over the characteristic equation, we can define the stability of system. But it gives only necessary condition. This necessary condition is not applicable to all the system. But so for example, this characteristic equation is given. So what necessary conditions are for stable system to be stable? All the coefficients that is a naught, comma, a1, a2 and so on up to an, these coefficients should be real and have the same sign as we can see in this characteristic equation. Second is, none of the coefficient should be 0. So all the coefficient should have a specific value, real value, and no coefficient should be 0. If it is happening, then system is said to be unstable. So we can see this is, we can draw the stability by inspecting the coefficient of this characteristic equation, and but this is not sufficient. It means it is not applicable everywhere, that where this condition, these two conditions are in favor and still we see system is unstable. So this is just necessary condition, but we cannot say this is only sufficient condition for a system to be stable one. Now let's see the stability. See, this characteristic equation is given to us and we can see all the coefficients here. A naught is equal to 1, A2, A1 is equal to 2, A2 is equal to 3, A4 is equal to 6, A5 is equal to 2 and A6 is equal to 1. So all the coefficients are present with same sign. There is no as such sign change. The system is stable. But if we see in this example, we observe that here this negative sign is coming, that is A1 is -2. So there is change of sign, so this system is unstable. Now we come to Routh stability criteria. Basically, this Routh stability criteria is having one necessary condition and one sufficient condition for the stability. And if a control system doesn't satisfy the necessary condition, we can say system is unstable. But if the system satisfies the necessary condition, then it may or may not be stable. Then we have to look for Routh criteria where necessary condition is being satisfied, but still the system is unstable. This Routh criteria is based on formulating an array which is called as Routh array. So, how Routh array is formed? First of all, just write the characteristic equation of the system and then fill the first two rows of the Routh array with the coefficient of the characteristic equation polynomial as mentioned in this table. So, I have listed out all the in column we'll start from the higher degree of s and move up to s raised to power 0, and we'll start with the coefficient. First two rows are filled with the coefficient given in this characteristic equation, like in this manner. A naught, then A2, A4 and so on. A naught, A2, A4, and then in second row the left out coefficients A1, A3, A5, and this is written in this way. And in these rows we are supposed to find these values B1, B2, B3, C1, C2 and so on. How B1 is obtained? This B1 is obtained by cross multiplication, like A1 get multiplied with A2 minus A naught multiplied by A3, and this is divided by A1. So, this is the value of this B1. Now, further this B2 is obtained by multiplying this A1 with A4 and then A naught with A5 minus A naught A5 divided by this A1 and so on. So, and B3 will be A1 into A6 minus A naught into A7 and divided by A naught, and we'll write all this obtained value in this row, and this is how this row is obtained. Then followed by how C1 is obtained. Then C1 will be obtained as multiply this B1 into A3 minus A1 into B2 divided by this B1. So, we can see here how C1 is obtained. Likewise, we can go for C2, that is B1 into A5 minus A1 into B3 and divided by B1, and we form an array based on the coefficients of this characteristic equation of the system. Now, after forming this array, we should have some conditions on the basis of which we call our system stable or unstable one. After designing the Routh array, first of all, there is no sign change in first column of Routh array. It means this is our first column A naught, A1, B1, C1 and up to AN, this column should have no sign change. If sign change is there, then system is not stable. So we can say our system is stable. And if sign change is there, system is unstable, and the number of sign change basically depicts the number of root lying on the right hand side of our S plane. So this is condition of Routh array, that is no sign change in first column. And second, if sign change, then number of sign changes is equal to number of roots on right hand side. So let us consider one example. See, this characteristic equation is given to us. So first of all, we have to design Routh array starting from S4, S3, S square, S1, S naught. So in this manner, we'll start creating Routh array starting with coefficient of S4, this is 1, then S square 3, S1 naught 1. In second row, it will be 3, second coefficient 2. So we have formed baseline of this array. Now we are supposed to find out this B1, B2, C1, C2, D1. Okay, so we'll find out all these value. So B1 is obtained by multiplying by 3 into 3 minus 2 into 1 divided by this 3. So we obtained this is as 7 by 3. Next, B2 is obtained by 3 into 1 minus 1 into 0 divided by 3. So we obtained this value as 1. So we have obtained this 7 by 3 and 1. Now how C1 is obtained? C1 will be obtained as multiply 7 by 3 with 2 minus 3 into 1 divided by this 7 by 3, as we can see here, and we get value 5 by 7. As no value is here, so we do not need to compute this value, or we can simply write it as 0. Now last value is obtained by multiply 5 by 7 into 1 minus 7 by 3 into 0 divided by 5 by 7, and we get 1. That is 7 5 by 7 into 1 minus 7 by 3 into 0 divided by 5 by 7 divided by 5 by 7, and we get this value as 1. After forming this array, we can see there is no sign change in first column. We are obtaining 1, 3, 7 by 3, 5 by 7 and 1. All the coefficients of this first column are positive with no sign change. So we can say this system is as stable one. Now let us consider another example in which this characteristic equation is given. Again, form Routh array for S cube, S square, S1, S naught. Write their coefficients 1, 1, 4, 16 and 4 into 1 minus 16 into 1 divided by 4. This is here no value is 0, so we can write as 0, and this we obtained as minus 3. Again we get 3 minus 3 into 16 minus 4 into 0 divided by minus 3, we get as this value 16. So we are obtaining the value of first column as 1, 4, minus 3 and 16. Now we can see here this is plus, but this is minus. So this is one sign change. Again, second sign change is first. This is second sign change, minus to plus. So here 2 times sign change is there. So we say this system is unstable, and the number of poles which are lying on the right hand plane is equal to 2. So this is how our Routh stability criteria is applied over a given system. Now moving further, we have one special case, we have basically 2 special cases associated with this Routh criteria, and our first case is when first element of any row becomes 0, then how that particular system is solved in using Routh criteria. So we can solve it by assuming a very small integer epsilon, which basically approaches to 0. So replace 0 by this small positive integer epsilon, and using this epsilon solve the whole stability, Routh stability criteria. So we can consider this example. Here in this, first of all, design Routh criteria S4, S cube, S square, S1 and S naught. Now go for putting the coefficients 1, 1, 1, 2, 2. Now here what we can do, as in this row 2 is common, we can simply replace it as by 1 or taking 2 common from this particular row. Now what we see, we observe that when we multiply 1 into 1 minus 1 into 1 divided by 1, this factor becomes 0. This 1 into 1 minus 1 into 0 divided by 1, here value comes out 1. So in this particular row, our first element is coming 0. So we cannot move further. Now we have to apply some tactic over here to solve this Routh criteria. Now replace this 0, a very small integer, that is epsilon. So considering this epsilon, we go solve the further Routh criteria, that epsilon into 1 into 1 divided by epsilon, and we get epsilon minus 1 divided by epsilon, and after this in last row we get first element as 1. Now if we just observe the first column 1, 1, epsilon, epsilon minus 1 divided by epsilon and 1, what we see, plus, plus, plus. Here we see if we put 0, this will become 0 minus 1 over 0, or it comes out as minus infinity. So whatever number we put here, we will get minus of sign. Okay, so here sign change is there. here we see there is one sign change, basically two sign changes are there. So this system is unstable. We cannot say this system is stable one. This is one way of solving this special case. What else we can do? We can also do this, replace S by 1 by Z. So we will having characteristic equation like this. One upon Z square 2 upon Z plus 1 is equal to 0. So this will become 1 plus 2Z plus Z square plus 2Z cube plus Z raised to power 4 is equal to 0. So our characteristic equation changes as Z4 plus 2Z cube plus Z square plus 2Z plus 1 is equal to 0, and form Routh criteria by using this form 1, 1, 1, 2, 2. So here we can solve in this way as well by replacing S by 1 by Z. So we have already defined this thing, hence system is unstable because we are getting minus infinity sign here. This is case number 2. In this case, the complete row of Routh array becomes 0. So we need to follow an extra step to solve this Routh array method. For this, we need to obtain one auxiliary equation, and that equation is just above that row which has become complete 0. Differentiate this auxiliary equation with respect to S and fill that row which has become 0 with the coefficients of this differentiated auxiliary equation. Let us understand this concept by considering one example. So this is our problem. This characteristic equation is given to us: S raised to power 5, 3S raised to power 4, S cube plus 3S square plus S plus 3. Now, if we design its Routh array, this will be 1, 1, 1, 3, 3, 3. Okay, 3, 3, and 3. So we can take 3 as common. We can simply write 1, 1, and 1. Now, if we find the coefficient of this row, 1 into 1 minus 1 into 1 divided by 1, this is coming out 0. 1 into 1 minus 1 into 1 divided by 1, again 0. So what we are observing, that our complete row has become 0. So we need to find out the auxiliary equation, and auxiliary equation is just above this row, this. So here we are having this row where highest degree of S is 4. So we can simply write our auxiliary equation as, that is, AS is equal to S raised to power 4 plus S raised to power 1 and plus 1. Okay, differentiate this equation with respect to S, we get 4S cube plus 2S. Okay, and we replace this row with the coefficient of this differentiated auxiliary equation as here 4 and 2. Take 2 common, this becomes 2 this become 1. Now we can solve the rest of the Routh array by using the same method. Okay, 2 into 1 minus 1 into 1 divided by 2, it comes out 0.5. Then 2 into 1, 0 into 1 divided by 2 is equal to 1. Further, apply the same method, 0.5 into 1 to 2 into 1 divided by 0.5, we get this value as -3 and last value as -1. So what extra step is here? Basically, extra step is just to find out auxiliary equation, and after applying auxiliary equation, if we still get complete row 0, then again define the auxiliary equation, and auxiliary equation is nothing but that the row which is just above the row which has become complete 0. Now we can see here our element of first column is 1, 1, 2, 0.5, -3 and 1. Again, sign change is occurring 2 times. One is here and second is here. +2 minus, then -2 plus. So this system is again unstable, and the roots which are lying on right hand side roots are 2. Okay, so these were 2 special cases associated with Routh array. So what are few advantages of using Routh array? First of all, system can be judged without actually solving the characteristic equation, and no evaluation of determinant is required as we have to perform in Harvard's criteria, so it saves our time. So it also provides the information of positive roots which are lying on the right hand side. In this we can also judge the relative stability, and we can find the critical value of gain or also frequency of sustained oscillation by using Routh criteria. This is used in basically root locus method, where we apply Routh criteria to obtain gain value and sustained frequency of sustained oscillations. We can also find the range of k, okay, and it also helps in finding out the intersection point of root locus with imaginary axis. But some disadvantages are also there. It is only valid for real coefficients, and it doesn't provide the exact location of closed loop holes in the left or right hand side of S-plane. It basically tells us how many roots are lying on left or right hand side, but it doesn't give their exact location. It is applicable to linear system only, and it doesn't suggest any method for stabilizing the unstable method. So this was all about our Routh criteria to find out stability of LTI system. Thank you and Jai Hind.